All right. So let's finish that lesson on the first law of thermodynamics with this last slide on reversible adiabatic expansion. Okay. So consider a reversible adiabatic expansion, and again, we're just going to limit ourselves to an ideal gas. You're going from P1, V1, T1 to P2, V2, T2. Okay. In a reversible adiabatic expansion, you should be able to show that P1 times V1 raised to the power gamma must be equal to P2 times V2 raised to the power gamma. Okay, so at any point along that uh, path, that particular path, the reversible adiabatic path, the product of pressure times volume raised to the power gamma is a constant. And that gamma right there is nothing more than just the ratio of the Cp to Cv for an ideal gas. Okay, so what is Cp for? What's the relationship between Cp and Cv for an ideal gas? Cp, remember, is Cv plus Nr. Oops. Cv plus Nr. Okay, and so Cp over Cv is just that, so it's just going to be 1 plus Nr over Cv, okay, right? So that's the ratio of Cp to Cv. Now, if you have an ideal monatomic gas, what is gamma? For a monatomic gas, ideal, what did we say Cv was? Remember? 3/2 R, right? 1 mole, that's per mole. And what is our Cp? Cv plus Nr. So on a per mole basis, that's going to be Cv plus R, right? So if we're doing per mole, we're going to put a bar over that. So what is Cp over Cv then? Gamma is Cv plus R over Cv, right? So that's 3/2 R plus R divided by 3/2 R. So that's going to be 5/2 R over 3/2 R. So R cancels out, so that's equal to 5 over 3, which is 1 2/3, so 1.66667. So okay, so that's gamma for an ideal monatomic gas. What is gamma for a diatomic? Well, Cv is just going to be 3/2 R per mole. That's a contribution from translational motion, right? Plus 2/2 R. Since it's a linear molecule, it's 1/2 R contribution from each rotational mode. So that gives you 5/2 R for your Cv. Okay. We're going to ignore the vibrational contribution. There should be an extra term there, but we can ignore that under ordinary conditions. Although we can get actual numbers, we can look at experimental numbers. So for something like O2, but good approximation would be Cv is 5/2 R. So what's our Cp going to be per mole? It's going to be 5/2 R plus 1 R. It's going to be 7/2 R. So what's our gamma for a diatomic ideal? It's going to be 7/2 R divided by 5/2 R. So R cancels out, 2 cancels out. What's 7 over 5? 1.4. Okay, so that's what gamma is. Okay. So anyway, let's go back to the question. you're supposed to show that P times V raised to the power gamma is a constant if you take a reversible adiabatic path. Okay? Let's imagine what that is. So imagine you have a gas right here. Okay, so you got an external pressure there. And let's just put sand on top of that. To make the process reversible, what do we do to make it expand? Okay, so you can approximate a reversible process by taking out 1 grain of sand at a time. Okay, so that would cause the volume to expand by an infinitesimal amount dV. But what would make it adiabatic? You have to prevent heat flow, so you have to have insulated walls, right? So it has to be adiabatic, so it's thermally insulated. So you take 1 grain of sand at a time. So that would be a reversible adiabatic. So you carry that out until you get to the final volume you want. So while this is happening, what's going to happen to the temperature of the gas? Okay. As you're taking out 1 grain of sand at a time, your gas is going to be expanding, right, against an external pressure. So work we expect to be negative, right? In fact, the amount of work involved for each step, for each infinitesimal step, the amount of work is equal to negative P dV, right? So we can say that that's equal to the small amount of work, so we use a D in front of the W, since we're looking at an infinitesimal change. Now, work, if you integrate dW, it will depend on what path you take. So dW is what we would call an inexact differential. And so to emphasize that it's an inexact differential, we usually draw a bar over the D. Okay, so dW, in this case, for each step is equal to minus P dV. What is dQ? For each infinitesimal step, what is our dq? Again, dq, just like work, is a path function. So if you integrate dq, it will depend on what path you take. So we usually don't put just a regular d in front of the q if you're talking about infinitesimal changes. What's our dq in this case? Adiabatic. What does adiabatic mean? No heat flow, right? So what's dq? 0. All right, so if dW and dQ are these for an adiabatic step, then what is our du? It's equal to dQ plus dW. All right, so du is just going to be equal to negative P dV. In this particular instance, you can use dW instead. You don't have to put a bar over the dW, since your dW is just going to be equal to du. Okay. Anyway, if you integrate du, what do you get? You get your delta u for that process. Okay. So du in this case is negative P dV. It's just equal to the work. Now, when you do this, what's going to happen? It's going to be losing energy, right? It's doing work. So what will happen to the temperature of the gas? What did we say last time about the relationship between temperature and U for an ideal gas? Delta U is just, U just depends on what? The temperature of the gas, remember? We said that delta U last time as a one consequence of Cp minus Cv being equal to Nr, we were able to show that delta U is just equal to Cv delta T, right? So du in this case then is just going to be equal to Cv dt, right? So here we have two expressions for du. Du is equal to negative P dV, and it's also equal to Cv dt. Now let's imagine that using a PV diagram. Let's visualize what's going on with a PV diagram. So here's your pressure volume diagram. So let's say this is P1, V1, T1. Okay. All right, so I'll have an isotherm right here for P1, V1, T1. So what's the temperature for this isotherm? It's going to be T1, right? Now, if it's going to be expanding and you're not letting heat flow in, it's going to be doing work, no heat flow, the temperature is going to be dropping, right? So what's going to be the isotherm for T2? Is it below T1 or above T1? It's going to be below T1. So T2 would be at a lower isotherm. So you would expect your P2, V2, T2 to be somewhere on this curve right here, on this isotherm. So let's just say this one right here is P2, V2, T2. Okay? So as you remove 1 grain of sand at a time, as you lower the external pressure so that your gas expands infinitesimally through a series of infinitesimal steps, what curve will you be tracing? You'll be going from P1, V1, T1 to P2, V2, T2, right? So that would be the path you're going to be taking from the initial state to the final state. That path, this path right here, okay, we call that a reversible adiabat. Okay, and for every point along that curve, you should be able to show, and that's what we're trying to do here, that pressure times volume raised to the gamma is equal to a constant. You'll notice that every point along the isotherm, pressure times volume is a constant, right? Is equal to nRT. So pressure times volume is a constant along the adiabat, along the isotherm, along the adiabat, pressure times volume raised to the gamma can be shown to be equal to a constant. All right. Now let's look at one of these infinitesimally small steps in greater detail and relate that to the expression that we have. Okay. Okay, so going back up here, we did say that du is negative p dv. So let me rewrite that over here. Du is negative p dv, but it's also equal to cv dt, right? Let me rewrite that. So, okay, let me write it closer. That's fine. Right there. Remember that this is just dq, dw, right? This is dw because your dq is 0. Okay. Let's interpret what these expressions, how these expressions relate to our PV diagram. Let's take a close-up of this thing right here. So if you have your pressure, okay, P1, okay, here's your pressure. If the isotherm would be like this, right? And your adiabat would be like this. So if we look at one infinitesimally small step, okay, then you're looking at, okay, so this is your adiabat. So let's look at one infinitesimally small step from here to here. So that change, let's say, if that's an infinitesimally small step, would be dv, right? And so this right here, okay, du for this one is negative p dv because dq is 0. Okay, for this step, direct step along the adiabat. Now we can imagine instead an alternative path. Remember, first law says it doesn't matter what path you take, you're going to have the same du, right? So if you take an isothermal path instead, okay? So if you were to instead take an isothermal path and then an isochoric path, so an isotherm and then an isochore to get to the same point, what's du for the isothermal path? Isothermal, temperature constant, U doesn't change, du is 0. What's du for the isochoric path? And that's just the cv dt that we wrote earlier, right? So negative p dv is equal to cv dt. So given that, let's just solve that equation now. Negative p dv equals cv dt. If you look at this, this is a differential equation. You've got two variables here that are expressed in terms of differentials, v and t. So if you solve this differential equation, what do you get? you get an equation that relates volume and temperature. Now, before we actually try to solve this, you have to realize that pressure here is not constant. It actually depends on V and T. So we have to express P in terms of V and T. How is pressure dependent on volume and temperature? Ideal gas law, PV equals nRT. So P is equal to what? nRT over V, right? And so we have that minus P dV is equal to CV dt. CV is a constant. It's 3/2 R or 3/2 nR for an ideal gas. All right, so you now have a differential equation that has only two variables, volume and temperature. What's the technique we use to solve differential equations? Separate your variables. Put one set of variables on one side, another set of variables on the other side. So we keep our volume on one side. Okay, so dV over V, I'm going to call this negative dV over V. And I'm going to move all my constants to the other side. So what do I have? I'm just going to make this positive. So I'll move all my constants to the other side. I'm going to have CV over negative nRT. Okay, so negative nR dt over T. Okay. Actually, I'd rather have it the other way. I'll move my constants back to the other side. Okay, let's do this. It's going to be negative nR over CV. Doesn't really matter. dV over V. Equals dt over T. Alright? Whereas negative nR over CV is nothing more than another constant. So let's just call that constant. Give me a letter. A. Okay, let's just call that a constant A. So I'm going to say A dV over V is equal to dt over T. You integrate both sides, what do you get? So you go from V1 to V2, and you integrate the other side from T1 to T2. What's the integral of dV over V? Natural log. So this is going to be ln of V. So there's a constant there. Evaluated from V1 to V2. So the left-hand side becomes A times ln of V2 minus ln of V1. What's the difference between two logs? It's the log of the ratio, right? So ln of V2 over V1. So that's your left-hand side. That's equal to, what do you have on the right-hand side? Natural log of T2 over T1 when you plug in the so the right-hand side becomes ln of T2 over T1. Okay. So now I'm going to simplify this. I want to try to get rid of the logs. What should I do? I'm going to move that A inside, right? So I'm going to say ln of V2 over V1 raised to the power A is equal to ln of T2 over T1. So now I can get rid of the logs. I can just say V2 over V1 raised to the power A equals T2 over T1. That's it, right? All right. Now, what's my, that relates, okay, what's my A again? Negative nR over CV. Let's express that in terms of gamma. What is negative n? Cp minus Cv is equal to nR, right? For an ideal gas. So I can rewrite my A. Let's do it this way here. A is equal to negative nR over Cv. But nR is just Cp minus Cv. So that's negative of Cp minus Cv over CV. So that's going to be CV minus CP over CV. So that's 1 minus CP over CV, or 1 minus gamma. So A here is just 1 minus gamma. All right? So I can rewrite my equation, this one right here. I'm going to use 1 minus gamma for A. So I'm going to say V2 over V1 raised to the power A, which is 1 minus gamma, is equal to T1 over T2 over T1. That's the relationship. Okay. Or I can rewrite this. I can also say that V2 over V1, I'm going to make this V1 over V2. I can rewrite this as V1 over V2. What would my exponent now be if I flip V2 and V1? Gamma minus 1. Why do I want to do that? I know gamma is going to be larger than 1, so I want that power to be a positive power. Okay, so it's equal to T2 over T1. Let's rearrange this. You can see that T1 V1 to the gamma minus 1 equals T2 V2 to the gamma minus 1. So that's how the two are related, temperature and volume. But what we're trying to do is relate pressure and volume, right? We were trying to show that P1 V1 to the gamma equals P2 V2 to the gamma. So how are we going to do that? If I don't want temperature in my expression, I just replace it. What's the relationship between temperature and pressure? PV equals nRT. So this is P1 V1 over nR, right? Times V1 to the gamma minus 1 equals P2 V2 over nR times V2 to the gamma minus 1. Okay, so can I simplify this now? P1, what is V1 times V1 raised to the gamma minus 1? That's going to be V1 to the gamma over nR is equal to, same thing on the right side, P2 times V2 to the gamma equal over nR. And you can just get rid of the nR. Multiply both sides by nR. It's just a constant. So you can say that P1 V1 to the gamma equals P2 V2 to the gamma. So that's your adiabat. In other words, when you plot your adiabat, okay, here's your isotherm. And your adiabat's like this. Okay. You have pressure versus volume. You can say pressure at any given point is equal to, okay, P1 V1 to the gamma, if this is point number 1, okay, divided by what? V2 to the gamma. So that's how pressure depends on volume on a reversible adiabatic path. Okay? So that's what happens to an ideal gas if you let it expand reversibly and adiabatically at the same time. Okay, so that's it for this lesson. We're going to move on to the next one.